So today's class let us begin the second module. Second module is on Laplace transform. So in today's class we define what is a Laplace transform and we will see the properties of Laplace transform. Now by a transformation we mean that's a function which converts one function into another. So transformation is a mathematical device which converts one function into another. And so example of a mathematical transformation is, so that is a differential operator. That's an example. So when you apply d on the function f of x, so d denotes the differential operator. So d by dx of sin x that will give us the new function cos x. So that is an example of a transformation. So we have an input function and we have an output function, and there is an operation which defines a particular transformation. So that so a transformation is any conversion from one function to another function. Now in Laplace transform, same way we will have a transformation of function f of t, which is defined for all t greater than or equal to 0. We will look at, so first we will define what is a Laplace transform. So we will see different properties of Laplace transform, and for some of the common functions we will be finding out what are the Laplace transform. A Laplace transform all functions will defined provided satisfy certain conditions, there will be Laplace transform exists. So main functions in the Laplace transform, and then we'll look at the inverse Laplace transform. We function Laplace transform. So if we are given the Laplace transform, we'll go back and find the original function. So that is done in the inverse Laplace transform, and these ideas are used for actually solving ordinary and partial differential equations. So main item Laplace transform application variable. So when you have initial value problems, so when you are given a problem together with a set of initial conditions, so we general solution general solution conditions substituted solution. So Laplace transform conditions particular solution arrive. So that is one of the applications of Laplace transform which we see. So it is used to solve ordinary differential equations and partial differential equation. So we can directly solve for initial value problem without substituting the conditions. Usually general solution in the particular solution directly particular solution. So that is the main application of Laplace transform will be seen in this module. So let us first define what is a Laplace transform. Let f of t be a function of t defined for all t greater than or equal to 0. Now by Laplace transform we mean is the operation given by integral 0 to infinity e power minus st f of t dt. So we have a function f of t which is defined for all t greater than or equal to 0. Then the Laplace transform is denoted by L of ft. Now L of ft is defined by, so L of ft is integral 0 to infinity e power minus st f of t dt. So provided this integral exists, we say that function has a Laplace transform, or the value of this integral is called as a Laplace transform. Now you can see that this is an improper integral. So the limit is infinity here. But all function integral exists. So provided this integral exists, we will obtain a Laplace transform for the function f of t. So here s is a parameter and s can take real or complex value. So this integral is called the Laplace transform. As you can see, you have an integral with with respect to the variable t, and here s is a parameter. So namukku kittuna value that is in general a function of s. So your input function is a function of t. This is your output value. That is a general function of s. And it is usually denoted as നമ്മുടെ ടെക്സ്റ്റ് യൂസ് ചെയ്യുന്ന നൊട്ടേഷൻ ഇതായിരിക്കും. സോ L of ft is denoted by f bar of s. So that is the notation for the Laplace transform. So it is usually denoted by f bar of s അല്ലെങ്കിൽ capital F of s. So that are the usual notations. Now look at the first property of Laplace transform. So that is called linearity property. So linearity property states that if C1 and C2 are constants and f and g are functions of t, then the Laplace transform of C1 f of t plus C2 g of t will be equal to C1 L of t plus C2 L of g of t. Now let us prove this. Proof is that uses the elementary property of integrals. So L of C1 ft plus C2 g of t that will be by definition Laplace transform, that will be integral 0 to infinity e power minus st C1f plus C2g dt. Now the integral has a linearity property, so this will be equal to C1 times integral 0 to infinity. The constant will come out of the integral, so we'll get e power minus st f of t dt plus C2 integral 0 to infinity e power minus st g of t dt. So that will be C1. So this is f bar of s plus C2 g of s. So that gives the required result. So this is C1 into Laplace transform of f of t plus C2 Laplace transform of g of t. Now let us look at the Laplace transform of few elementary functions. Now the first function we'll be looking is the Laplace transform of 1. So by definition that will be integral 0 to infinity e power minus st into 1 dt. Now upon integrating e power minus st, the integral is with respect to t, we will get e power minus st by minus s from 0 to infinity. So that will be e power minus infinity will be 0. So we will be getting 0 minus e power 0 is 1 by s, and we will be making the assumption that s is greater than 0. If s less than 0 anengil e power infinity varum, that will become infinity. So we will be considering the case when s is greater than 0. So this will be 1 by s. So that is the condition for the convergence. So provided s must be greater than 0, then L of 1 will be equal to by s. So L of 1 is equal to by s if greater than 0. Now let us find the value of L of t raised to n. So L of t raised to n is given by n factorial s raised to n plus 1, where n is a positive integer. So if you have the positive powers of t, so L of t raised to n is n factorial by s raised to n plus 1. So let us write down the integral for L of s to n. So this is integral 0 to infinity t power n e raised to minus st dt. Now if you substitute st equal to x, that give us, so we will get s dt equal to dx, and x will be varying from 0 to, so that is integral 0 to infinity. Now t will be s by x whole power n e power minus x. Now dt will be dx by s, so that will be, now integral is upon, sorry, here t will be x by s, vary. So we will be getting 1 by s raised to n plus 1 integral 0 to infinity x raised to n e power minus x dx. Now if we look at this integral, so integral 0 to infinity x raised to n e power minus x, that is a gamma function. So this will be equal to 1 by s raised to n plus 1. The integral is a gamma function, so the value of the integral will be gamma n plus 1. Now since n is a positive integer, gamma n plus 1 will be n factorial, so n factorial by s raised to n plus 1. So that will be the value of the Laplace transform of t raised to n. N is a positive integer. Let's look at the Laplace transform of e raised to at. So by definition it is integral 0 to infinity e power at power minus st dt. So that is integral 0 to infinity. Let me take the power rendu ഒരുമിച്ചെടുക്കുക. So that will be e power minus of s minus at dt. So this will be e power minus s minus a t minus s minus a from 0 to infinity. Now I will be taking the case where s minus a is greater than 0, so that is s greater than a. അപ്പോൾ നമുക്ക് e power minus infinity വരും. This will be 0 at the value infinity. At t equal to infinity നമ്മൾ ലിമിറ്റ് എടുക്കുമ്പോൾ നമുക്ക് ഫൈനൈറ്റ് വാല്യൂ വരണം. സോ the integral converge when s is greater than a. So that is going to give, so get 0 minus 1 by minus of s minus a. So it is going to give 1 by s minus a, where s is greater than a. So that is the value of Laplace transform of e raised to 8. So e raised to 8 will be 1 by s minus a. Next we will look at the Laplace transform of sin at. So that is again integral 0 to infinity e power minus st sin at dt. Now the value of the integral will be power minus st by s square plus a square minus s sin 80 വരും minus a cos 80. Now apply the limits from 0 to infinity. So e power minus infinity, we will be assuming the case where 0, so e power minus infinity 0 വരും. So at infinity we will be having 0, and at 0 e power minus 0 1 വരും, 1 by s square plus a square, and at t equal to 0 we will be getting minus a. So that will be a by s square plus a square. So that the Laplace transform of sin at will be a by s square plus a square, s is greater than